everyone. Welcome to the plenary session. Before we get started introducing our next speaker, I just want to make an announcement. The business meeting, because of the COVID rules that had us eating lunch outside, we had a compressed period for questions. And I know many of you wanted to speak in the business meeting, which is one of the important things we always like to do in our town hall. So the SIG chair and the program chairs and the general chairs are going to be available in this room at 3 p.m. until 3:30, basically for the second half of the town hall, for the part where anyone in the community who wants to speak and get answers to questions about the SIG will have an opportunity to do that. So if that interests you, come here at 3 p.m. That being said, let's turn to the main event here. So it's a real joy for me to have the opportunity to introduce Michael Jordan. He's one of the most famous and influential researchers at the interface of machine learning and statistics. If you don't believe me, he has 250,000 citations and an H-index of almost 200. That's insane. And he has literally been called the Michael Jordan of computer science. By Science magazine, but you know, who's counting? But beyond these kind of high-level numeric points, he's a really influential and deeply interdisciplinary researcher. He got a bachelor's in psychology, a master's in math, a PhD in cognitive science, and now has a joint appointment at Berkeley between EECS and statistics. So it only makes sense that he would now be turning his attention to economics because it's basically the only thing left. His research interests, according to his webpage, don't even mention economics, although that now in the last kind of 5 years has been a major focus for him. But he lists computational, statistical, cognitive, biological, and social sciences. He's generally been identified with the viewpoint that machine learning needs firm statistical foundations. He helped to popularize Bayesian networks, variational inference, and the expectation maximization algorithm. Lately, he's been arguing that machine learning needs to focus on problems in decision-making that go beyond simple prediction, which I think is the sort of jumping-off point for the work he'll be speaking to us about today. I could list his awards, but it would just be silly. He's a member of essentially every professional society that you've heard of: the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences. He's a foreign member of the Royal Society. And I could just go on and on. Maybe the best way to see it is that some of his students are, just a huge list of his students are superstars in their own right. So he really has just started a whole dynasty of thought leaders in machine learning. So it's really great that we have him here today to hear about his viewpoint on economics and computer science. Thank you.
Thank you. So that was a fun introduction. Thank you, Kevin. I appreciate it. So it's traditional to start by thanking the organizers for inviting you, and I want to say that I really thank the organizers for inviting me. This is a community I wanted to be part of and belong to for a few years now, and so this is a great way to do that. I do have a message, I think, which is particularly appropriate for the younger people in the room, so I want to get to know many of you, not just the older people. Let me just skip the title and move on to the, you've got to get me fixed up there. There we go. One button was all that was needed. Now, I need this thing to be working. Last day hiccups. Maybe it needs to be just turned on. All right, that was it. Okay. All right, so as Kevin alluded to, so I want to tell a little about why I'm working in the topics I'm working on. I'm a machine learning person and statistical, really. And it's because a lot of the real-world problems I see out there require a blend of these three foundational disciplines, okay, and equal measure somehow: statistics, economics, and computer science. And they already have sort of been blended, of course. Algorithm and game theory, which this community represents, is that blend. But older blends are well known. Machine learning really is a blend of statistics and computer science. It's not just a statistical perspective on something. Every idea that I can think of in machine learning was already present in statistics, every single one. And it's been deepened by machine learning people, but it was already there, going back to the 40s and 50s. And people keep rediscovering ideas that were present in the 40s, 50s. Stochastic gradient, the big workhorse, that was 1950s, by statisticians, so on. And the theory was present and so on. Well, the third one, what is that? Well, like econometrics really is statistics meets economics, and it's mostly about measuring the economy and worrying about causal inference and trying to infer things about the economy, mostly for macroeconomics. All right, so you can see where I'm going, kind of. You know, econometricians don't worry too much about computer science, mostly. This is all a bit of a caricature. There's not a lot of depth, you know, combinatorial depth in econometrics. Algorithm and game theory people here have started to think about statistics, but I don't see the sophistication I'm kind of used to about uncertainty quantification and so on. And I think that's changing. And then certainly machine learning people have not really worried too much about economics. Incentives are not present in most every single machine learning paper, and it creates problems in the real world. All right, so the point then is that emerging problems blend all three, and this is something all of you already believe and know. But the other point I want to make is that, you know, our founders, people like Blackwell, von Neumann, Arrow, Wald, and all that, would have totally got this. They were in all three fields. They were really mathematicians, but they didn't distinguish among these fields. Blackwell certainly was a statistician. I got to know him, luckily. But he did a lot of work in computer science, and he did certainly a lot of work in economics and beyond. And by the way, this triad, also control theory and applied math, are all kind of part of it. But these perspectives of computation and inference and incentives have to be blended. Okay, so let me jump a little bit more into machine learning, which is this blend of statistics and computation, and say a little bit more about what it is. Well, there's at least two sides to it. There's pattern recognition, find patterns in large amounts of data to make predictions. It's become the hyped up entity of the era. It does make predictions really, really well. But if you think predictions solve real world problems all by itself, then you're missing the boat. And that's what I want to kind of get into a little bit here. So the other side, what's the rest of the boat, is decision making. Okay? And decision making is not just thresholding the output of a prediction system. And that is the naivete of a lot of machine learning researchers. They think if they build the world's best prediction system, that it'll solve the world's problems. It doesn't. So think about, you go into a doctor's office and you have to make a decision about your health. And suppose in 5 years, say the doctor's got now a big black box, it's a neural network that has been trained on all the world's medical data, from all humans, all hospitals, all situations, et cetera, et cetera. You know, the ultimate prediction engine for medicine. So it does a really good job of predicting. All right, are you kind of done? Is it do the medicine for you? And the answer is definitely not. So suppose the output of one of that, you know, they measure 100,000 variables about your body, including your genome, your height, your weight, your blood pressure, goes into the neural net and out pops some predictions. So one of the predictions might be a prediction about whether you're going to have a heart attack, you know, in the next year or not. And if some number is over 0.7, you're likely to have a heart attack based on the historical data. So your number is 0.701. What does that mean? It's certainly not a decision. What you're going to say, your first thing you're going to say is, well, give me some uncertainty quantification. How sure are you of that number? Where was the data gathered? Was it gathered on people like me, or was it gathered on different kinds of people? Was it gathered 10 years ago? Was it gathered recently? What kind of machines were used? That's kind of like provenance in database language. Where is all this stuff coming from? So it's not just a little error bar. It's not just a little Gaussian error bar, a bootstrapped error bar. It's uncertainty and the way we think about it as human beings. What's the uncertainty here? Can we reduce that uncertainty somehow? Let's do some counterfactual thinking, doctor. What if I were to exercise more? What if I were to eat better? Also, you'll remember all kinds of facts about your life that you hadn't remembered before. For example, your parents had maybe heart disease, or you had asthma as a child. Maybe that's relevant, and so on. So you now realize that that prediction box had none of the above in it. It didn't have any of that data in it. And so now when you're in the act of decision making, you're trying to bring new data to bear that wasn't relevant before. And that's where the prediction perspective falls down. Data becomes relevant in the moment of making a decision, in the context of making that, in the closed loop with a person who's interacting with you and reasoning through a problem. Okay, so I probably don't have to, you know, I'm sort of pushing on this a little bit because it's not that common for machine learning people. And I'm giving you guys ammunition for when you talk with these machine learning folks to kind of answer them. Because you will get them saying, yeah, a perfect prediction, that's the end game. It's not. All right, but particularly, I just told you about now one decision. Should I have heart, you know, operation or not? But it's never one decision. I made 45 decisions today on different time scales, involving my trip, involving, you know, my family, involving all kinds of things. And they all interact with your decisions. Our healthcare clearly interacts. It's not just treat me, it's treat all of us as human beings. If there's a pandemic in particular, it interacts in all kinds of new ways. It's not just a prediction from the past. So it feels much more like a market to me. It feels much more like a statistical market, where it's a market structured by data analysis, by the flow of data on planetary scale, and how to kind of use that data to structure a good market. That's the problem of the era. Okay? It's not AI, it's not put intelligence in a computer, it's not put thought in a computer for sure. It's build big systems that can actually kind of act like good markets in a statistical sense. All right, so if you go back to pattern recognition, you ask the pattern recognition folks, what are the big problems of your era? You know, backpropagation, stochastic gradient are working really well, and it's being scaled and all that. Well, they say, yeah, we agree. Uncertainty quantification, we're still not doing that very well. They're doing it terribly, so that's an understatement. We also have issues with robustness and adversaries, and you're probably seeing a lot of this research. There's biases and fairness issues, and there's explainability, interpretability, and so on and so forth. Right, those are all big problems, and they are the ones that bite you in the real world. But these aren't just technical, how do you adjust the neural net a little bit, and how do you add a little bit of a cost function. These are problems involving economic concepts. These involve interactions, incentives, people, social contexts, and so on. And involves all the counterfactuals and so on and so forth. Okay, so the bigger perspective is one that pulls these into the broader perspective of decision theory, game theory. All right, so I think I've said enough on this one. Decisions are not just about thresholding prediction systems, they involve scarcity and competition. I want to dig into this a little bit. This was the thought experiment I did about 10 years ago when I was in China. I started to kind of watch neural nets and, well, machine learning systems being rolled out in the real world. They would become a commodity. You could download a recommendation system and build a business model around that. So people were doing it wildly. And it was fun to watch. So I saw things like, you know, predict, do a recommendation system for restaurants. Sounds like a pretty cool idea, because nowadays, when I went into Shanghai, and I said, it's 6 p.m. and I don't speak Mandarin, I was by myself and I wanted to have, a good meal. You're not going to go to the, Google or Baidu or whatever and say, good restaurant in Shanghai and get anything reasonable, okay? And you don't want to do that. You don't want to be involved in browsing in that moment. You want to be in a market. Hey, I'm available for meals. Anyone want to serve me a meal? So you want just more like Uber. You want to push a button and say, geolocate me. Here's some stuff about my past that's relevant. I like Sichuan cuisine. I have a certain price point, and here's my location. And that goes as a bid to the other side of the market, which are all the restaurants, who look at all the bids coming in and make offers. Well, this is not how people were thinking. They were building recommendation systems, and they were recommending, individually to each person that came into the recommendation system, just like with movies and books. Well, so like with movies and books, Amazon, Netflix and all, they recommend to, hundreds of millions of people a day. And they recommend individually to each one of them using their big prediction engine. And they could easily recommend the same book to, 100,000 people. That happens all the time at Amazon. So they just print the book quickly. It's called print on demand. And certainly with movies, you just copy the bits. So the mentality was often, there's no scarcity. I can just copy everything I need quickly enough and I can serve everybody. Computer science will make scarcity go away. All right, well, you guys know that's just not true. And so the restaurant example is a good one. I watched in Shanghai as a certain app started to get popular. And as soon as everyone in Shanghai is using it, you can make a recommendation of the same restaurant to 10,000 people. And things like that happened. And of course, with the routes to the airport, if you route everybody down the fastest route, it no longer becomes the fastest route. Again, stuff that's common to you guys, but not common to people thinking in the mindset of recommendation systems. And so in fact, the mindset is so bleak, it's so misguided at times that, the mindset is that, I don't know who, I don't want to recommend, 10,000 people to the same restaurant. That's obviously bad. It's a load balancing problem. I'm going to recommend only 45 people to this restaurant and 30 people here. And who decides who gets to go to what restaurant? Well, I, as the search engine, do, because I know everything about you, just like when I make ad recommendations. Just based on your browsing history, I know enough about you to say which restaurant you really most want to go to. And so that's how they were thinking about it. And that's how I think people think about, also like routes to the airport. We know which route you prefer to take because we know enough about you. And that mindset is not just wrong, it's bad. But it's very much present in the mind of Silicon Valley people. All right, so how are we going to fix this? Well, we create markets. It's kind of, in some sense, obvious. Diners on one side, restaurants on the other. we have bids, we have a little bit of history. So it's not just that we know the preferences already when we do a matching. It's rather, hey, I've been eating Szechuan food in the past. Hey, my friends eat this other cuisine. Hey, there's a social network that informs my preferences. I also do exploration, exploitation to try some restaurants. That all is part of the system that I would like to be participating in. All right, so you see that in that language, there's kind of a blend of recommendation systems meets matching, meets statistical uncertainty, meets social networks, and so on and so forth. And that's a system that if you were to build that, it would be great. You would make huge amounts of money, and it would really work if you really did it right. Does anything like that exist? Well, there is something like this exists, so I'm going to quickly mention this. This is United Masters, which is a company based in Brooklyn. CEO is Steve Stout, who's a friend of mine, brilliant person, and he already had this perspective as a non-scientist. He's been a music producer, and he's famous in the hip-hop world, very well-known person. And he and I met up about 7 or 8 years ago and started talking about this, and we both had the same perspective, which is that music business is broken because it's not a market. You think, why? Well, there's more songs being listened to than ever before in history right now, by a factor of 100. More songs being written than ever before in history by a factor of 1,000. But here's the amazing thing. If you look at the data on any given day, 95% of the songs being listened to were written in the last 6 months and by people you never heard of. So it's not that everyone's listening to Beyonce and the Beatles and so on. Who's doing all this? Well, it's a lot of 16 and 18-year-olds who are creating songs on their laptop and are really good at it. So good that everyone's listening to that music. It's very fresh, it's very exciting. Right? So it sounds great. It sounds like there must be a wonderful market. Of course, there's not. These kids are not making any money. What are they doing? They're sending their songs to SoundCloud, and then services like Spotify are grabbing the songs, copying the bits, and then streaming it to people, and economic value is not accompanying any of that. Okay, so economic value then gets restored later on by Spotify creating an advertising or subscription business, but it has nothing to do with the actual people who created the producers of the music. Occasionally they take some money and throw it back at a few of the influencers just to make it look like they're doing something socially with social welfare, but they're not. All right, so this is a system, United Math system. It's a platform, it's a company that builds a market using data, and it really works. So all it does is that it provides connections between producers and consumers. The platform mediates that. It's a little more like Uber. So if I'm a musician and I'm making popular music, I get to see a dashboard at the end of the week, and I get to see there's a dot every time one of my songs has been listened. It's a map of, say, the United States. And I learned that, I didn't know this, but in Boulder, Colorado, I'm popular. And I'm popular because 10,000 people listened to my music last week in Boulder. So I showed that to the venue owners in Boulder. They invite me, I come and give a show, I make $20,000. I do that 3 times in a year, I have a salary. And this is not just fanciful, this exists. So 2 million musicians are now on this platform, 2 million, and they are making salaries, not just a little bit of money, they're making salaries. And a lot of that's coming because there's a third part of the market, it's a 3-way market. There's also brands. So the National Basketball Association is one of the many brands in that third part of the market. If you go to the NBA site right now, Steve knows the NBA people. He made a deal with them where when you go watch a clip of the NBA, there's music behind it. And that music used to be, Kanye or whatever, and he would get more money. But now it's United Masters artists. And so every time one of the clips is watched, an artist gets paid. It's a salary, it's a contract. All right, so we in this room can build systems like this. If we go into the real world and we say, oh, it's a market building problem. Who are the producers, who are the consumers? Where should the economic value be? How should it be realized? How should it flow? You could do this, so this is 2 million people in the US. You could do this in China, you could do this in Africa, you could do this in Brazil, and it will happen. You could do it not just with music, but with other forms of art, with information, with journalism, and so on. Okay, with that as background, that's the kind of things that motivated and still to this day motivate me to be involved in building these kind of systems. I think that computer science, we kind of owe it to the world. We got some things right, search engines we got right, a lot of other things we got wrong, social networks. So we have to start thinking about how to make things better in a builder sense, not just fix up the little problems, the patches. All right, so this is a slide I prepared maybe 7 or 8 years ago of kind of problems to work on at this interface. Again, I was talking in ML crowds, relationships among optimum equilibrium and the dynamics using stochastic processes, which we know a lot about now, like Langevin and dynamic systems. And then markets where you have to explore to learn your preferences, they aren't given a priori. Multi-way markets in which you have recommendation systems, I already alluded to that. Uncertainty quantification has got to be the underpinnings of all of this. If you don't do that well, you're going to make a mess. Mechanism design with learned preferences, a lot of you work on that. Contracts and statistical experiments, I'm going to talk about that today. And incentive-aware X, Y, and Z. Trade-off between various social quantities and technical quantities. At some point, someone pulled me aside and said, that's a great slide, Mike, really that, it's kind of, you're being a thought leader for the ML community, that's great, but there's this community called EC that already does all that stuff. And so I said, oh, who's EC? I admit, so I found out, and that's about 5 years ago, and I, of course, started learning. I watched Tim Roughgarden's lectures, I did all the wonderful things that one does to learn a new field, which I always love. But I do want to bring some more perspective to this. I do think that statistics is not really a first-class citizen here. And a lot of times you'll see kind of theoretical machine learning, online learning, which I believe in, the David Blackwell style. But there's much, much more to statistical inference than what I see here already. So that's what I'm hoping to kind of help bring to this community is a deeper and better. And so that's what my agenda was 20 years ago to all the ML people. They didn't know anything about statistics. I said, you got to learn some statistics, and that's happened. But I think here also the payoff will be even bigger. Let me just say that there's some progress, and this is work in my own group, that I could have talked about. I've decided not to, but this is what I've actually worked on in the meantime in the last 15 years. We have a real strong, deepened understanding of gradient-based optimization. We as a community, but my group has worked a lot on this. We know how to escape saddle points in high dimensions. So we can do non-convex optimization. I can guarantee you miss all the saddle points in 100,000 dimensional space, and I can give you a rate of that, and it's a favorable rate, and I have upper and lower bounds on that, okay? So that's a string of papers. There's one in the Journal of the ACM we did about a year ago. We have a way to analyze all this with continuous time, and continuous time reveals much more of the phenomena, the topology meets dynamics, than discrete time. So in computer science, we often think in discrete time, everything is algorithmic in discrete time, but as physicists know, you go to continuous time, you can get a lot of insight. So there's phase transitions that happen in continuous time that don't happen in discrete time. And we see them when we analyze. And so our main tool there is something called high-resolution differential equations. These come from fluid mechanics, and they're not just take a limiting, a step size to 0 and you get an ODE. This is richer than that, and they have strong algorithmic consequences. So we can distinguish between algorithms that are different in discrete time, that if you take a naive limit, they collapse to the same ODE. Now we take these new limits, they stay separate, and we learn things in that field, and then we discretize back to get our results. We use symplectic integration. That's a technique from geometry. We also have similarly a very strong now theoretical understanding of stochastic gradient methods in high dimensions. Theory of underdamped longitudinal diffusions. We have upper, lower bounds, and we have rate retrieving algorithms there too, and again, they're favorable. We know how to do Thompson sampling with longitudinal diffusions. And we have now theory of stochastic extra gradient, and that's kind of under active development. And then lastly, I may mention at the end of the talk, we have a new perspective on uncertainty quantification. It's not classical Bayesian, and it's not classical, bootstrap. It's something a little bit different. And it's really working at large scale, and I want to maybe allude to that. It allows you to get risk control, not just error bar. And it gives you things like predict not just an object, but predict a set of things that object could be, and give me a guarantee that the true label is in that set with some probability. We can do things like that. Okay, so anyway, if you were interested, these are all in the archive, and you can see them. Every one of them has theory in them, rates, often lower bounds. Instead, I decided to do something dangerous, which is come and tell you about stuff that's in your own field that I'm now still learning about. So be gentle with me. But I want to talk a little bit about contract theory meets statistics. So the goal in all three of these is to take something serious from statistics and put it in contact with something serious from game theory or mechanism design. All right? And it may not be the perfect way, or maybe not, but I think it's revealing to sort of try to do that. And of course, there'll be economics, computation, statistics, all three of them present in each one of these little vignettes. Okay, so again, these are all papers on the archive, and I'm not going to get into the mathematics here, but I'm going to allude to it. But you can see the theorems in the papers. Okay? So we'll talk a little bit about contract theory, then a little bit about strategic classification, a little bit of an older topic, and then I'll talk a little bit about matching markets and bandit feedback. And I see Alex here is one of my collaborators who can help me to get that right. Okay, so this is a very new topic. We've been working on this for about 6 months now. This is what colleagues Stephen Bates, Michael Sklar, and Jake Soloff, Stephen and Jake are with me at Berkeley, and Michael's at Stanford. So how many of you know what contract theory is, just out of curiosity? So this group, it's about half. It's not everybody. That's a little bit surprising. I asked in a big meeting in statistics last week in London, and 0 people out of this same size audience knew what contract theory is. 0. And I've also asked in AML communities, and it's a little higher than 0, but not much. So it's surprising. So contract theory is kind of the second branch of mechanism design. If auction theory is one, contract theory is the other. And I think for economists, they're equally viable, equally important. They're both kind of old, but they're being refurbished. We're going to bring statistics into contact with contract theory. All right. So, I think as most of you know, and I won't spend much time on this, but, contract theory is kind of the classical version of it is there's a principal and there's some agents. The principal wants to get the agents to do something, act in some way that's beneficial maybe to them, but also beneficial to the principal. And the agents know something the principal doesn't know. And the agents are not willing just to tell the principal about that. And so the principal can start to think about it as try to get information out of them, or just try to get them to act in some way, even though the principal is not going to ever learn what the agents know. All right, so if you Lafont and Marimo is a really great read on this, and you've all been on airlines where there's both economy class and business class. That's contract theory at work. So you want to do price discrimination, but you can't just discriminate on the basis of the way someone looks or their history. So you just write a little contract. There's a menu of 2 options. Either you can get a cheaper fare and you have no services, or you can spend a lot more money and you get the same services plus a little cup of red wine. And amazingly, there's lots of people who are ready to spend a lot more money and get that little cup of red wine and be treated specially. And so the airline's happy. They fill some of their seats with these high-ticket items. The people are happy because they love this prestige. And then the economy class people are happy too because they pay a cheap fare and they don't give a damn about the little cup of red wine. All right, and so the social welfare is very high, much higher than setting any fixed price, and it is doing price discrimination, but it's doing it in a legal way. All right, so anyway, it's a beautiful topic. So we're going to do this in a statistical setting. So we're going to, so here's our motivating example. The FDA, Federal Drug Administration, is trying to decide what drugs to put on the market. So they're the principal, and how they decide? Well, they take a candidate drug and they do a clinical trial at great expense. They have to decide which clinical trials to do and how much money to invest in that clinical trial. All right? And the goal is, of course, then to produce drugs that really do work. Vaccines. The agents are the drug companies, and they have a drug to propose, and they'd love for the FDA to test it out, and they could just ask, please, test it out, and the FDA might do that. There's some chance of a false positive, that when the FDA tests it out, even though the drug doesn't actually do anything, it's, useless, there's a false positive that the drug gets approved. And then the company can make $1 billion for a little while until someone comes up with a drug that actually works better and people start to realize that. Okay, I'm not thinking about drugs that hurt people, just drugs that don't work. There's plenty of them on the market. So how do you do this? How do you think about this problem in a both statistical and economic way? All right, so first of all, I want to emphasize this is big money. So clinical trials, as you all know, are being run all the time. Some of you may have participated in them. And you can see the millions of dollars over there on phase 1, phase 2, and phase 3 for various areas of medicine. So ongoing, immense social investment. All right, so how do we think about getting rid of the false positives and false negatives here so that we actually do this right? So we have both incentives, we also have statistical control, error rates. All right, so let's think about now as a statistician. So a statistician comes into the problem, and he says, oh, it looks like, it's basically a Neyman Pearson test. I've got a bad drugs, good drugs. So let's say the type is 0 if I have a bad drug, again, meaning a drug that does nothing, not effective, and 1 is a good drug. And I have false positive rates, and I have false negative rates. So if I approve and it's a bad drug, I want to control that false positive at 0.05, say. I also have a false negative rate, which I'm here controlling at 0.2, so the power is 0.8. So standard numbers in a lot of biostatistics applications. So now the question is this a good statistical protocol? Well, it has mini-max properties, blah, 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 but is it actually good? Well, it depends on the money involved. So let's imagine in one case that it costs $20 million to run the trial, and if you do get approved, market analysis suggests you'll make about $200 million. So kind of typical numbers. So now let's do a little simple calculation using that table of numbers. The expected profit you're an agent sitting there thinking about this, expected profit, given that I have a drug which is actually not effective, which I don't really know, but I have more information, I have some information, maybe I've done my own little internal trial, but given that the drug is actually not effective, the expected profit is minus 10 million. So you can do the little calculation. And so I look at that and I say, well, it's not worth it, okay? The FDA runs, given the setup, they run all their tests and everything, and the approvals are all going to be good drugs. So that's pretty nice. But what if we just change the numbers a little bit? Suppose it costs you still $20 million to run the trial, but if you get approved, you make $2 billion, okay? Aspirin or whatever. So now you do the same calculation and you get the expected profit is 80 million. All right, so now you look at that because there's a false positive chance and you make a lot of money out of it. So now you look at that and you say, okay, I'm going to throw lots of drugs at the FDA. And so there are situations where this happens. All right, so what do you do here? Well, you need contract theory. So contract theory comes to the rescue, but it's got to be done in a setting where the menu of options reflects the Neyman-Pearson test. So that's a little different than classical contract theory. All right, so here is the contract setup. The private information is denoted as the theta, and you give the agent, each of these mini agents, an opt-in protocol. They can either not do this at all, or if they opt in, they first of all pay our dollars. And then secondly, they choose a payout function from a menu. And so this is like the business class, economy class. There's a set of options, and they pick one of those options. They're going to pay a certain amount of money, and they're going to get a certain amount of money back. Our task is, as in usual contract theory, to design that menu. And then what's new is that a statistical trial will yield a random variable z, which is drawn from a probability distribution that depends on the true theta, okay? Because nature knows the true theta. And so a trial will be run with, say, random people, 36,000 people, and we'll get out some z. And then we'll do statistics with that, okay? So the agent at that point will receive the payoff f of z because that was promised in the contract. And then the principal receives the utility that depends on the f of z, but also depends on the true theta, because this is going to go out into the full population, and we're going to know whether it really works or not. All right, so the agents act to maximize a certain payoff. That's their best response in this situation, okay? Under expectation under the random evidence z. All right, so if we're going to bring incentives into that, let's talk about the minimal kind of incentive alignment we need. We need that if you're a null agent, a bad agent, all right, then the utility of the principal in that case is less than or equal to 0, okay? And it's decreasing in this sufficient statistic f of z for all of the points in the null set. And then on the other hand, if you're a good agent, the utility from the point of view of the principal is positive and it's increasing in this f of z. All right, so now you want to set up a menu, all right, that respects that incentive compatibility story, such that you transact as much as possible with the agents who have actually good drugs to offer you. Okay? There'll always be some swap, but you want to do this as much as possible. All right, so you define a contract as menu incentive aligned in just this obvious way. You take the expectation of the payout you're going to have to give minus the money that they had to pay to play the game, and you need that to be less than or equal to 0. Okay, now what can we say more about this? Can we characterize this in any way other than just making a definition? And here it turned out to be a bit of a surprise. So there's a notion in statistics called an E-value. It's not a P-value. It's something different. It's recent discovery in statistics. An E-value is just a random variable, a measurable mapping, that has an expectation which is less than or equal to 1 under the null hypothesis. So it has a little of the flavor of a p-value, which is a tail probability under the null hypothesis. This is an expectation of a random variable. If that is true, then you're called an E-value for some hypothesis space. All right, and we have proved a theorem which says that we now relate the contract theory to the statistics. It turns out that a contract is incentive aligned if and only if all of the payout functions are E-values. Okay, so this proof has a little bit of flavor of the Neyman-Pearson lemma. It's kind of an economic version of Neyman-Pearson lemma. You can see that in the paper. Now we do the real statistics, which is that we don't know the true theta. All right, so how do we build a menu if we don't know the true theta? So now we go to something, we do maxi-min or mini-max. All right, we say, well, okay, we don't know the true menu, but let's imagine, well, there is a distribution. Let's call it Q over theta. And therefore, the actual utility in a range of experiments the FDA will run will be an expectation additionally under that Q. All right. Maxi-min optimality would be to find a contract, that would be the design variable, to maximize the minimum of the utilities. Okay, so that's a standard statistical ploy at this point. It's not Bayesian, it's maxi-min. All right, and so now we have another theorem, which is that a little deeper, but a menu is maxi-min if and only if it's contained in the set of all incentive-compatible contracts. Okay, in other words, it's contained in the set of all E values. Moreover, there's an easy corollary to see that larger menus only give you more power. They help the non-null agents, while still controlling the error rate on the null agents. So the biggest menu possible, for statistical reasons, is better. Now for interpretability or computational reasons, a smaller menu might be preferred, but statistically the bigger one is preferred. So that means that we now actually have a full characterization. The set, the optimal design, is the set of all E values. Okay, so that's a connection between contract theory and statistics. Okay, it's an if and only if. Okay, so that was some theory. How is this going to play out in practice? Well, first of all, I don't know. This work was done in the last 3 months, and we'll see. We're working actually with the FDA, but I think there's going to be a broader set of applications. So here's just one that we have a paper from 3 days ago there on the bottom. So I didn't prepare a lot of slides here, but this is with Praneeth Karimarati, Mwenchuo Guo, and myself. And so we're doing this in the federated, we're doing something like this in the federated learning situation. So here, federated learning is kind of, Google wants to build a central model which is really, really good, and they have all these agents on the edge, and they're gathering all this data from them to make a better model than any individual agent could make. And the agents are somehow supposed to be happy because the overall model will be served back to them later and they'll be happy. But again, if you're an economics mind person, you sort of say, wait a minute, where are the incentives here? And let's think about this economically. So we've done that in this paper. We adapt this theory. So in fact, when people roll these kind of things out, free riding becomes a huge issue. Kevin sees me supplying all this data. He says, well, I don't have to supply any data. I don't want to, the privacy risks are too big. I'll just let someone else do it. All right, so anyway, we adapt our theory to this problem. We have now an incentive-compatible mechanism using E-values that incentivizes agents to contribute a maximum amount of value of data. So there's been some work on contract theory and federated learning, but it's more about trying to get the private type information out of the agents. We're not trying to do that. We're trying to just incentivize them to send a lot of data. All right? A key tool here is statistical accuracy shaping. All right, so at some point you have to face the conundrum of how do you evaluate the quality of data? Kevin's sending me some data. He says it's really good, and a lot of the literature says, well, it's a function of the number of data points. Well, no, it's not a function of the number of data points. It's a function of the quality of the data. How do you measure that? All right, well, there as a statistician, it's pretty natural. What I'm going to do is take 5 people in the audience, and we're all going to play a game together. All 5 of you are going to give me some data, incentivized hopefully. I take the data, and this is data for a particular purpose. It's not just data. It's for predicting whether someone's going to default on a loan or not. All right, so I have some test data, and I'm going to do cross-validation. I'm going to take 4 people, build a model, and then see how well I do on test data, and then bring Kevin's data, add it to the list, and see how much better I do. So it's a little bit like VCG. It has that flavor, but it's more of a statistical leave one out kind of calculation. And so I can now say, well, I don't know how you got that data or what you did with it. Maybe you added noise, but I can tell you your data is worth some amount. I can put a number on that. And I can do that for all of the 5 players, and now I can give them back answers which are a function of the quality of the data they sent me. I'll give you a bad answer if you sent me bad data. So you're incentivized to send better data. All right, so there's kind of the hook. Anyway, if you're curious, I encourage you to have a look at that. Okay, so let me turn to something, again, where statistics really comes in contact with economics. Strategic classification with Tiana, who's a student with me at Berkeley, and Eric is now a professor at Caltech. So this is about 5 years old or something, where this little topic. Moritz Hart wrote with colleagues a very nice paper that helped crystallize this, even though it had been around for a while, as most things are. And it's just the problem that a lot of you are aware of. If you're doing decision making in the face of strategic agents, they're incentivized often to lie. So, if I'm filling out a health insurance thing, and if I know that if I seem healthy, I'll get a lower rate, then I'm going to try to seem healthy. Okay, and so this is Goodhart's law in economics. If I design some measure of something like poverty index score, it looks very nice and Gaussian in 1994, and by 2003, it looks very non-Gaussian because people are lying to appear to be more poor than they otherwise were so they can get some benefits. Okay, so in general, you have these feedback loops in learning. And so, this is something machine learning people are going to have to start facing. It is really just game theoretic. But it's a special kind of game. So it's a game where the agent's best response is to give some data, and it might be data that's strategic. They may lie. That's what agents do. And so let's take that into account. We're going to try to make it hard for them to lie. So instead of just saying, do you exercise a lot, we're going to measure, did you pay money for a health club or something? We're going to try to make it a little hard. But we're going to allow them to give us strategic data. Then we're going to build a predictive model centrally, and we're going to tell you what kind of methodology we're using, say logistic regression. We're not going to give you the parameter values, but we're going to tell you what methodology we're using. Why? Well, maybe for regulatory reasons, probably, but also maybe it's a good business model. The agents will trust us if they know what we're doing. We send back a model, the agents look at that model, and I say, oh, I see, if I were to change my data a little bit in this way, I might even do better. That loops, and there you have a Stackelberg game. But it's a special kind of Stackelberg game. It's a statistical Stackelberg game, where the best response of the decision maker is to build a statistical model. So that's not an arbitrary Stackelberg game, okay? And there may be some principle there, like maximum likelihood. Okay, so what can we say about these Stackelberg games? All right, well, one of the first things you have to do in a Stackelberg game decides who's the leader and who's the follower. It matters, okay? And you get different results whether someone's the leader or someone else is the follower. And it's not always the leader is the best thing to be. Sometimes the follower is the best thing to be. All right, well, let's study that in this situation. All right, first of all, we have to think about the timescales involved. And we're used to thinking about arbitrary timescales like continuous time, so we don't like to be locked into these synchronous kind of algorithms. And here, in fact, I think it makes no sense to have a synchronous algorithm. The agents and the principal are distributed, and they think on their own way and their own scale, and it may be strategically beneficial to go slowly or to go fast. And so let's let that be a degree of freedom in our thinking. All right, so what we're going to do is now have different timescales for the agents and for the central decision maker and see what the consequences of that are. All right, so here the agents are responding quickly and the central decision maker is responding slowly, and we could do the opposite. All right, so when does this ever happen? Well, when does it happen that the decision maker is slow relative to the agents? Does that actually happen in real life? And of course the answer is yes. This is really the classical situation, say of college admissions or credit scoring. The college takes in a bunch of applications. They don't look at every application and then adjust their criteria. Okay, they publish a model every couple of years and they update it slowly for obvious reasons. Similarly with credit scoring. So we call that the proactive situation. There also is the flip it around where the strategic agent now goes slowly. Why would that happen? Well, that's very common. That's the internet. YouTube, after everybody has an interaction with them, they adjust their algorithm, at least in principle. They have infinite computational power. All right, so there has been some theory on this from an economic point of view, and it's known that this situation where the decision maker is fast gives pretty high welfare to the decision maker, and it gives bad welfare to the strategic agents. Okay, so Google's happy with this, but no one else is happy. All right, so we thought, well, okay, what happens when we flip it around? All right, so we proved a couple of theorems. First of all, that if you change the update frequency in these ways, there are Stackelberg equilibria in both cases, and they are different Stackelberg equilibria, so that's the first theorem. But the second theorem is the more interesting one. It turns out in this statistical best response situation that when the strategic agents are the ones who lead, okay, the welfare is higher for the strategic agents, but it's also higher for the central decision maker. Okay, so that's a bit of a surprise, all right? So it's higher for both. It's a win-win to have the strategic agents be the ones who actually lead in this situation, okay? All right, so this is true, not of an arbitrary Stackelberg game, definitely, but it is a new theorem in game theory if you want. It's of a special kind of a statistical Stackelberg game, and by that I mean a class of, say, generalized linear models. So we have to specify a model family, and then this result arises, okay? So to still be explored about how general that is, but for a broad class of statistical problems, it's true. Okay, last part of the talk. Kevin, how am I doing on time? All right. Okay, so this will even, I think, be more familiar to many of you. I know several of you have been working on this particular topic where we have bandits meeting matching markets. So I thought I'd finish with this just because your brain can relax a little bit. And I didn't want to get to this result that Alex is one of the developers of. A Lyapunov function for matching markets, okay? Because one of our tools in dynamical systems and learning systems is always a Lyapunov function. It's not just you're stable or you're not, all right? It's something that quantifies how unstable you are. And so once you can do that, we have all kinds of tools that allow you both to analyze but also bring data to bear, to optimize, and so on. So that's where I want to get in this last part. Okay, so we want to bring some learning ideas together, statistics ideas together with economics. Multi-arm bandits, again, it's not new to machine learning. It was a statistician's idea back in the 50s. But you have rewards coming from each of these arms. There's an unknown reward distribution, and you'd like to maximize the expected reward, okay, the mean of the reward distribution. And as you probably all know, there is a regret analysis of this where you compare yourself to an oracle who knows the best arm a priori and always picks that. And you can get logarithmic regret relative to that oracle with an algorithm such as upper confidence bound that simply puts a little bit of statistics. It has a large deviation style confidence bound on the mean reward, so it covers the mean reward with some probability. And then you pick the upper confidence bound to decide which arm to choose on the next trial. And the upper bound is appropriate for both exploration and exploitation. Why would that upper bound be high? Well, maybe the whole distribution is shifted over to the right. It gives you high rewards in general, so you should pick that arm. Or maybe the whole confidence thing is really, really wide. That's why it's really high. So you should pick that arm to explore, decide whether it's actually, get more data, decide whether it's a good arm or not. So anyway, beautiful analyses of this now in textbook treatments. You also all know what matching markets are, so let's start with the Gale-Shapley version of this where you have no monetary transfers, but we do assume that the preferences are known a priori. Given known preferences listed by both the buyers and the sellers, then something like deferred attachment will find a stable matching. And as a learning person, I look at that and I say, well, great, and I can see why the Nobel Prize came out of that and everything, it's beautiful, but I say, well, when and how do you actually know the preferences a priori? I just did college admissions with one of my kids, and I can assure that my kid did not have a ranking of preferences over all the universities at all. And I can assure when I go to Shanghai and look at all the restaurants, I do not have a ranking of preferences over the restaurants, and so on and so forth. So we're always learning and exploiting and exploring in life to find our preferences. And we also interacting with other people. There's a social way to learn our preferences. So we need to bring those into the matching market. Okay, so we want matching. So here is a first thought experiment. Matching markets meet bandit learning. There is a little literature. I know some of you have written papers here. I don't want to say we did something particularly seminal here, but we did start to look at this. We built a framework in which you had competing agents. In our framework, if on a given trial they picked different arms, then no problem, they both get their reward. But when they picked the same arm, in our framework, only one of them got a reward, the other got no reward. Okay, so it's not the same as a congestion channel, where if both of you pick it, you both get kind of diminished performance. Here, one of you gets perfect performance, gets to see the full reward, the other sees no reward. Okay. So who gets the reward? Well, the other side of the market is also running an explore-exploit trade-off, and they, for whatever reason, arm 2 prefers the bear. So I look, the human looks at that and they say, I see, I like arm 2, but when I pick it, the bear also seems to like it, and when the bear picks it, I lose. The arm seems to prefer the bear. So I'm going to have to explore some of the other arms more than I otherwise would. All right, so in that statement, you recognize you're going to pay some regret for the presence of competition. Okay? Other people, or agents in the game, will cause you to explore more than you otherwise would. You must be some enhanced regret. And by the way, did I not mention my collaborators here? It's very important for me to do that. Let me go back. Here we go. This is with Lydia Liu, who's now taking a postdoc with John Kleinberg. I don't know if John's here, but anyway, Lydia's great. And Jorge Amani is a postdoc at MIT. They were students at Berkeley. Okay, so there's our competing agents. And so now we have a bandit market in which you get noisy rewards, and if you overlap, only one of you gets the reward. So what's the story here? So let's do a regret analysis. We have to define the oracle, and the oracle is pretty straightforward. It's just suppose we knew all of the mean rewards a priori, and we gave those to the Shapley algorithm, to stable marriage algorithm. Okay, so we call the regret relative to that the stable regret. And there's a pessimal and an optimal version of the stable regret. Here's a particular algorithm you can analyze, and we did. It's just Gale-Shapley meets UCB. So instead of giving the mean rewards, which you don't know, to Gale-Shapley, you give the upper confidence bound to Gale-Shapley. Okay, and so that's a merger of the two ideas. And so there we prove a regret bound. And our regret bound, here's regret as a function of the number of trials n, is still logarithmic in n. Okay, so, we didn't lose anything by having competition. That's actually a little bit of a surprise. Where you get hit is that delta squared, and that is a measure of the gap among all of the agent's rewards. Okay, so if you're very close to some other agent, delta will be small, and you will get a worse regret, but it's only a constant. Okay? Okay, so that was with Lydia and Horia, and then Mina and Alex and Yixing came to Berkeley as first-year students. Yixing was a postdoc, and Jacob is a faculty colleague. And we're already interested in matching markets, and we're interested in the one with transfers. And in fact, when we wrote that paper, Lydia and Horia and I, and sent it to EC, we got rejected because they says, who cares about matching markets without money? Maybe that's how you guys think, but... So we said, fine, and went and moved on. Then Alex came and says, no, we got to think about money. And so this paper goes further in allowing the Shapley-Shubik model, where you have monetary transfers, more like Uber. Uber, you have a matching between a rider and a driver, but the driver pays the rider pays the driver. Got that backwards. Okay, so we'd like to now find these market outcomes that align with user preferences on two sides of the market, while we're simultaneously learning from data. And so this paper was a little bit more of a go up the abstraction hierarchy a little bit to say, what does it mean to learn these preferences? Okay? All right, so we're going to do this with transfer utilities, and the first goal then is not just say you're stable or you're not, but to get a measure of instability. Because if you have a quantitative measure where it's 0 when you're stable and it goes up from there, or vice versa. Because then you can go downhill with gradient-based algorithms, which we know and love. Okay, so here's the quantitative measure of instability, and I especially late in the talk, I'm not going to explain it, but if you stare at it for a moment, it should look a little bit like, Shapley index, or a little bit like VCG. It's kind of got the first term is a maximization over agent-specific utilities. The second term is the same, but it's got also the transfers tau in them, okay? And then the outer maximization is over all subsets of agents. So there it has a very much of a Shapley flavor. And Alex and Mina were able to prove that if you didn't have the outer maximum, this will fail. Okay, this will not be an actual measure of instability. Okay, so if you now take this quantity here and treat that as a primal problem and look at the dual of this, it turns out it has a very nice economic interpretation. And so what it is, it's the minimal amount of money an outsider could add to the market to make the system stable. Okay? So if you're used to thinking about stability or not stable, and you have money, the money can make this quantitative. You can say, well, it's unstable, but could I add some money to make it stable? And this is very natural from a control theory or numerical analysis point of view. We have an instability, and we don't want to be unstable. So how hard is it to get to stable from unstable? And that's like condition number in matrices. Okay, so these are quantitative measures of how unstable you are. Okay, so we propose that as a measure of instability, a Lyapunov function that you can go downhill in, and you can use that to derive the logarithmic regret bound in the previous paper. Okay? Okay, last 2 minutes. I'm done with the talk. You can now, this is now dessert. I'm going to do like 3 slides on, this is advertising for this new framework on uncertainty quantification. Because I don't know how much all of you care or know about uncertainty quantification, about getting uncertainty in your algorithms, but I hope you will care more and more over time. And we've had a little bit of what I think is a bit of a breakthrough here. This particular paper I want to mention is with Anastasios and Stephen with me at Berkeley, and colleague and friend Manuel Candes and Li Wale at Stanford. And this framework builds on something called conformal prediction, which goes back to Vladimir Vogt in the 1990s, and a few people in statistics community picked up on it in the last few years. It's becoming a thing. There's now a little mini conference on it. It allows you to take an arbitrary, complex state-of-the-art model like a neural network that produces predictions but has dubious uncertainty quantification. And that's true of neural nets. They say, well, I think the probability of it being a bunny is this number, the probability of it being a horse is this number, and those numbers are pretty much uncalibrated. All right? Same thing though with Bayesian methods. You can have a very complex, big Bayesian recommendation system. It'll output some numbers. It'll put posteriors on those, but those are meaningless posteriors because someone put an arbitrary prior. Okay, this methodology allows you to calibrate those. It puts an extra layer, doesn't change anything inside the system. No more partial derivatives are calculated, nothing. It puts an extra calibration layer there and turns those numbers into actual calibrated statistical coverage. numbers that cover the truth with some determined probability, okay? All right, and I'm not going to get into how this is done, but there are now tutorials and papers on the web that do this. I just want to say that at the end of the day, our approach is we do this not with just kind of squared error, but we do it with arbitrary risk functions, so this is decision theoretic, and we reduce it to a one-dimensional functional. There's a way of doing that, and now you have a knob you can turn, and you get nested sets of predictors. So this is tumor prediction up there. We have a lot of false positives, false negatives at the top, and then a lot of false positives at the bottom. And the Goldilocks zone in the middle is where the knob is set in the best way. And the way to set the knob is, there's a new theory we have that basically uses concentration ideas to take the fluctuating risk and to take the, have it bound the true risk and pick a place to set that knob. So just to let you know, this exists, and it's really actually pretty simple. It kind of has a quantile flavor. You take some values and you find quantiles of a certain distribution. That's what makes it distribution free. Okay, so I'm going to show you two examples and I'm done. So this is one which just takes AlphaFold, this kind of breakthrough protein structure prediction algorithm from DeepMind. It's a big, big black box that takes in proteins and predicts structures, but with no uncertainty quantification. So that's not going to be good in the future for drug design. So we just took that black box and we made a calibration layer. And we just did that. And this slide sort of reports on our results there, and you can see the details. So we calibrated AlphaFold. The next slide is really pretty cool. This is state-of-the-art object recognition and vision. If you haven't been following computer vision, you can take a camera and point at this room and basically find everything in the room, okay? But when there's lots of occlusion and lots of moving parts and all that, it starts to break down a bit. And you need uncertainty quantification to talk about that, especially in the medical domain. So the slide I'm about to show you is a state-of-the-art system from the point of view of predicting the object. It's just the state-of-the-art neural net, but we put uncertainty quantification on top of that. So for every object in the scene, it's not going to just have a single label, it'll have a set of labels. So it could be a kangaroo, it could be a wolf, it could be this. And in that set, I can guarantee you the true label is there with 95% probability. That's a statistical theory. Okay, so I'm going to show you that. So this is an outdoor scene. And you can see all the fluctuating little labels there. Traffic light is just a singleton. It's pretty sure about that. But car, truck, bus, it's not so sure. So it gives you a set. And the size of the set gives you some idea of magnitude of uncertainty, but the actual set is informative. It tells you what it's likely to be. Similarly for outdoor scenes where there's huge amounts of clutter. And okay, so when you start to think about uncertainty quantification, you can go to a classical, Gaussian book, take Gaussian limits, linearization, or you can go bootstrap, and I want you to know there's something else. And I think this is particularly appropriate for some of our large machine learning systems. Okay, so I think I can move on. So I did this here early in the talk, and let me just make a couple of more comments about this. This was kind of an academic person's perspective, but a lot of my perspective is informed by being out in the real world and doing some consulting with, say, Amazon and Alibaba and China and all that. And so I want to emphasize that. And I want to emphasize that this has led to a view on what's happening right now is that we're just all computer science, and we develop the latest, coolest algorithms and make them better. Or why are we doing what we're doing? Okay? And especially when this buzzword AI started to get used for everything in sight, which I really resented, because it's not AI. It's not putting thought in a computer and making it like a human being, like a baby. We haven't achieved that at all. That was the original uses of AI. So we're using it in a new way for anything intelligent subject with computers. But I don't think that's a very good way to think about what it is. And so here's the way I think about it now. It took me 40 years to think about this. But if you go back and look in the 1930s, there was nothing called chemical engineering. It didn't exist. There was chemistry, there was quantum mechanics. So you knew what happened when you put a couple of molecules together to make new molecules. You could predict, and you could do it with test tubes. And someone at some point said, well, why don't we build huge systems, factories out in the fields that produce chlorine or plastics or whatever? Can we do that? And they tried, and of course it didn't work. They had to develop new ideas. New thermodynamics was needed, new scale, new fluid flow ideas. And it was still very, very hard. And new mathematics was needed. And that emerged as a field called chemical engineering in the 40s and 50s. Okay? Big change to our world. That was my father was a chemical engineer. In the 1950s, that was the cool thing to be. Now it's computer science. Then it was that. Right? And they did change our world. Everything we're wearing, all of our computers, all comes from that, the ability to make plastics and things. All right? And there were some externalities, but people worked on it. It was important. All right. Same thing with electrical engineering. Before like 1900, there was no electrical engineering per se as a field, but there was Maxwell's equations already. So there was an understanding of electromagnetism, but you didn't know how to electrify a city or bring power into your house and not burn it down or build circuits or whatever. And so a field had to emerge, which is now called electrical engineering. And it has its own mathematics. So when you say it's engineering, it's not just engineering. It has its mathematical principles. But they're often about building things and making modules and scaling and being protective and safe. So I hope you see where I'm going. That's what's happening in our era. We have these proto-fields of computing, algorithms, inference, and economics. Mostly they're used to analyze systems that exist, all right? Or occasionally build something and throw it out there and hope it works, like an old factory that people tried, all right? But what's really happening is we're trying to build these planetary scale systems that do transportation, that do healthcare, that do commerce, do all the things. And what's new about this branch, and so that's the engineering version of statistics and theory of computing. Put those together with economics, and you now a new engineering discipline. And that's what machine learning people, I think of themselves as doing. All right? And when they get a lot of money from VCs, they actually try to build the factories, and sometimes they fail and sometimes they work. Right? But if you're going to build a system that really works for large numbers of human beings, and it's safe and predictable and fair and all of that, then you got to think at this high level of what system am I building? What's the inputs? What's the outputs? What's the failure modes and all that? And I think that's what's happening. So the machine learning, I think, is the buzzword in AI now that got attached to that human entity. And it'll take 2 or 3 decades like it did with these previous branches of engineering. So anyway, hopefully that's useful to you, especially for the younger people in the room, to think about what are we doing and why are we doing it. Hopefully that helps.
Well, thanks for a great talk that spanned the range of giving us a new lens of looking at the vision of our field, down to an entire day's worth of technical talks and even some dessert before lunch. I think we might have a few minutes for questions. I'm looking at the program chairs to see if they give us the thumbs up. Okay, so let me invite anyone with questions then to come to the microphones here so that you can be heard on Gather. We'll also try to look at the chat on Gather to see if there are questions that people have there. So if you've got a question, just come stand at the microphones, and if we get a line at both microphones, we'll alternate.
It's a very quick one. Can we have your slides?
I have my slides. Yeah,
Yes.
Just pay me enough and I'll give them. Yeah, you could do it systematically if Kevin would, if there's a way to do that. Right?
Yeah, sure. We'll find a way. If you pass them on to me,
or just hit me with email. I might respond.
Thank you.
we'll find a way.
Yeah.
Thank you for your talk. I'm interested in what's your opinions on the common knowledge in the games. For example, in your information illustrations in the federated learning setting, it seems like everyone.
I missed the first word, the first adjective.
The common knowledge in games. Common knowledge in games.
Commonality in games. Common knowledge. Thank you. Yes.
And
common knowledge in games. Yeah.
So in your information illustration example or papers, it seems like every agent know that they are playing the same games and know how does the principal use their data to improve the predictions, and whether that's feasible in practice, I'm not very sure.
Yeah, so great question, and there's tons of questions that each one of you could ask about information flow and about signaling and all kinds of real-world things that, first of all, I don't know that much about, and secondly, we've thought about, but we don't really have it in our current things. And there's some amount, we've been somewhat clear about common knowledge at times, so that, for example, that work on federated learning, it's common knowledge on how much it costs to gather data. There's kind of an agreed upon metric there. That's used in the algorithm. If that were not true, we'd have to do something else, okay? But that said, I really like the contract theory perspective in that it really does allow, these moral hazards or, these adverse selection situations where someone doesn't know what I know and we don't have common. We just face the issue that we don't have much common knowledge. But so we only have common knowledge about the overall structure, which might come from regulatory reasons or it might come from business models. Yeah, no, it's great. So I just maybe encourage you not to be super adversarial in your work, right? Because at the end of the day, a lot of the work in economics that's had a huge impact on real life is because there's also a regulatory agency sitting there making a few rules of law that keep people break at their hazard. So it's not really related to what you just asked, but just to highlight that I think You know, especially when there's uncertainty and everything, we just have to cope with that, and we do. And we cope with the fact that I don't know if you're a bad guy with a gun, you know, but I cope with that. And I do that with uncertainty. And so, you know, thinking about how humans navigate all this mess of markets we are involved in and all this uncertainty, I think helps just bring you back to the zone we want to be in. We want to also, in my little triangle, there's not lawyers there, but they should be there because eventually it's critical to have the right kind of law structuring some of these things.
Great, well, let's leave it there because we're already a little late for the scheduled start of lunch, but let's thank Michael again. And I hope this will be the beginning of